And our first presenter is Vincent Fortuin. He's a tenure-track research group leader at Helmholtz AI in Munich and a faculty member at the Technical University of Munich. And he also holds several fellowships and additional affiliations. His presentation will be about recent advances in deep Bayesian optimization for scientific AI.
Cool, thanks. Yeah, so thank you all for coming. I mean, I know it's always a bit tricky on the last day to come for the first session, so thanks especially for that, and for not going to the foundation models, but to the hardcore math session in the morning. Also, thanks for the organizers for inviting me. I think it's a great conference. I've had a lot of great interactions, and I've talked to so many people that I partially lost my voice a bit, so I hope you can still understand me well. Today I'm going to talk about Bayesian optimization. So we've seen a lot about AlphaFold over the last few days, right? So people have kind of talked about how this really heralds this age of AI for science. So one thing that I've seen a lot in collaborations with people is that they were very excited about AlphaFold, and then they were like, oh, we also want to do this kind of deep learning stuff now. But they found that it didn't really work that well, right? And I think one of the reasons is that a lot of scientific data sets are quite small compared to AlphaFold, right? So like most of the data sets that people work with are really in the small data regime. So we've heard like the protein database was like built over decades for like $50 billion, right? But like a lot of people don't have $50 billion to build themselves a big data set and train a foundation model. And I see that a lot in my own collaborations, right? So if I work with people in medicine, they might have very unique patient cohorts, so on the order of tens of thousands of patients, or in material science, they have like these very special lab equipment, right? Like the machines that they actually built themselves, so they're the only ones who have this machine, and they can generate data that nobody else can generate, or even in astrophysics where they observe very rare events, right? Like on the order of hundreds of exoplanets with like a few telescopes that we have. So essentially the question is like, how can we do AI with these small data sets, right? If we don't have the big data that you need to train a foundation model. And what I want to propose is that if you can select your data cleverly, you can actually get away with much less data, right? So like if you come to me with already a collected data set of 1,000 points, I can't do much. But if you let me help you select these 1,000 points, then we can go quite a long way, right? And so this whole sequential learning idea is to collect some data, then fit your model, adjust what you want to learn from the data, and then based on that collect more data. So it's akin to this lab in the loop argument that we've been hearing also in some previous talks. And one way to do this is to use Bayesian optimization, right? So Bayesian optimization is a black box optimization method where here you have this surface of a function that we want to optimize, and we don't have gradients, right? So we cannot do gradient descent. We can only query the function at certain points, and then based on that decide where next to query. And the Bayesian way is to have a posterior over functions, and then based on the uncertainty in that posterior decide where we might want to query next. So it's really this trade-off between exploration and exploitation, right? So we, on one hand, want to query at points where we believe it could be good, but also we're at points where we don't know yet, right? So like there might be a lot of good function values, and we just haven't seen them yet. So one method that people often use as a surrogate model for Bayesian optimization are Gaussian processes. Some of you might have heard of that. In Gaussian processes, you have this kernel. So you can essentially design how smooth you want your function to be or whether you want it to be periodic, but otherwise they're relatively limited, right? So what I want to argue for is to use Bayesian neural networks. So in Bayesian neural networks, you essentially don't have a fixed setting of parameters, but you have a distribution over parameters, right? And so you also get a distribution over functions. And as you know, neural networks are universal function approximators, right? So Bayesian neural networks are also universal function distribution approximators. So we can really capture any distribution over functions you might want. And it's been shown in some related work that's very excited by some people that just published this last year, that in higher dimensions, Bayesian neural networks actually can work quite well on Bayesian optimization. So the way to read these graphs is higher is better, right? We're trying to achieve a high reward. And the yellow curve you see is a Bayesian neural network, right? So we see, especially as the dimensionality grows here on the one side to 6,000 dimensions, the Bayesian neural network really quickly gets the top reward, while the Gaussian process and other methods don't. So we've done some work where we try to understand why that is. So this was led by Agustinus here. And we've shown that if you use a certain type of approximate inference, so in this case Laplace inference, which are the blue and purple curves, you can learn much faster than if you use, for instance, deep ensembles, right? So you might know deep ensembles are a kind of popular method to get uncertainties. So it's just you train several neural networks and then you use this ensemble of several methods. And you see the deep ensemble is the green and red curves. And if you use the Bayesian approach, so the blue and purple, especially on the very right data set here, you get a much faster convergence to a good function, right? So we were kind of motivated by this to look a bit more into Bayesian optimization with BNNs. Now, one question we often got from practitioners was, okay, but we have our Gaussian process priors that we've built over time, and we maybe physicists have some clever physical model that they've already formulated as a Gaussian process kernel. So they might ask, how can we get that prior knowledge into the Bayesian neural network, right? Because in a neural network, it's much harder to write down your prior knowledge over parameters or something. So we had a student, Tristan, here, who worked on using Gaussian process priors and BNNs. And so the reason, because why this image looks the same as on the previous slide, is that essentially, it works perfectly, right? So the functions you get are essentially the same. So you can use any Gaussian process prior you want, slap it on your Bayesian neural network, and you'll get a prior over functions that looks exactly like the Gaussian process prior. And so this allows you to then use the whole inference toolbox of neural networks for the posterior, but still use your Gaussian process priors that you might have developed. We did that in a physical example. So here we look at ocean drifters. So you have some buoys that are swimming on the ocean, and you track them with GPS. And based on the movement of all of these drifters, you want to figure out what's the field of ocean currents, right? And so people have very clever physical prior knowledge about how ocean currents work. So they have designed very intricate GP kernels. And we could show that here with our method, which is the FSP Laplace, so function space Laplace, we get essentially the same performance as a Gaussian process and much better than standard Bayesian neural network methods. And we've also shown this for BaseOpt, so this is what this talk is about, right? So again, in Bayesian optimization, we get as good performance as GPs, or even better in some cases with these methods. And Tristan has now worked on actually bringing this into practice. So this is a paper we currently have under submission in collaboration with some actual material scientists, where we showed that if you use this for material science, so our method is the very right one again, you get a much faster and much more robust convergence, right? So what you also see here is different runs, and you see that in our method, all the runs are much closer together than in the GP, for instance, where you have more variance over the different runs. Okay, so this is one way of getting your prior knowledge in, right? If you already have a Gaussian process prior, you can write it down like this. What often is the case is that your experts, maybe some of you are the experts, right? They have prior knowledge that is very hard to write down in a succinct form, right? So you can tell me for each data point, maybe in the material science case, you can tell me for each molecule how much you believe it to be a good material. But then if there's a billion molecules, I don't want to sit you down and ask you a billion times for each molecule, right? So one thing we thought about is that in this Bayesian optimization loop, essentially we don't need you to say this a priori for all the molecules, but it's okay at each step to look at a few molecules we might test next and then just ask you for a handful of molecules, right? So essentially it's a kind of this lab in the loop thing is the black thing, but then as an expert you sit there and every now and then you get asked oh, maybe the next molecules are one of these kind of 5 molecules, which one of the 5 do you like better, right? So this is what we call asynchronous prior elicitation, right? So we don't elicit the prior in the beginning, but during the whole process. And we've also shown that this can really drastically improve performance. So the solid lines here are with the expert in the loop, and the dashed lines are without the expert. So one interesting case that is maybe interesting for some of you biologists, so this is a protein design task. So in protein design, you often have this problem that either you can build proteins that are very good, but they're boring because they look exactly like the ones you already know, or you can build proteins that are very novel and interesting, but they don't work. All right, so you have this kind of trade-off between novelty, which here is on the x-axis, and the fitness, which is on the y-axis. So essentially, we want to go as far as possible to the top right corner, where we have proteins that are novel and fit, right? And we see, especially in the bottom row here, that the red points, which are ours, are quite up to the right. And here we used biological prior knowledge, right, which allows us to then create very novel proteins that still work because we essentially don't naively create bad proteins, right? And so like don't have time to go into all the prior knowledge, but we used all these knowledge that people have about the similarity of amino acids, so these amino acid kind of replacement matrices that then tell you that if you have a protein that already works, maybe a similar one might be replacing a certain amino acid with another one that's similar, as opposed to replacing it with a completely different amino acid, right? So it's not rocket science, but like some of these like very simple priors can already go quite a long way in these applications. Is maybe the bottom line. So yeah, I have to close soon. One last argument I want to make, and that's because a lot of people tell me, oh, Bayesopt, it's a bit complicated. There's hundreds of papers at these machine learning conferences that all have their own Bayesian optimization algorithm. And as a biologist or domain practitioner, I don't know which one to use. So just to give you a bit more confidence, I want to say that if you use kind of very standard vanilla Bayesopt, it actually works quite well often. Right, and so this was work that was led by my student Ben, who's sitting over there. Like we took a lot of these kind of modern, state-of-the-art algorithms that people publish in all these machine learning conferences, and we just compare it to a well-tuned, vanilla version of standard upper confidence-bound Bayesopt that's been around for 30 years. And actually, the standard thing like works quite well, right? So you don't need all these fancy modern stuff. In a lot of cases, you can just use the good old-fashioned standard approach, and it'll get you there. Okay, so to end, if you want to learn more about Bayesian neural networks, we wrote a review paper on this. So if you're fast enough, you can scan that QR code. Otherwise, I'm sure you'll find it on my website or wherever. We also wrote a position paper at ICML last year that makes a case for why Bayesian deep learning is really needed also in this age of large-scale AI. And so that's going to talk more about the connection to foundation models and language models and these kind of things. And also a relatively recent position paper on generative AI in general and how that all connects. So with that, I'll summarize. Essentially, what I wanted to convey to you is that you can actually get away with much smaller data sets if you choose the data points intelligently. And you can use Bayesian neural networks for that, and especially in higher dimensions that often outperforms these Gaussian process surrogates that people have been using before. And they allow you to incorporate a lot of your scientific domain prior knowledge that you all have in different ways. So thank you, and looking forward to your questions.